Yeah, thank you very much for inviting me. I'm going to speak about testing for uniqueness of estimators. And I will give a short introduction into the setting we will be using, and also some kind of motivation why we are going to use this type of setting. Then I give an overview of the hypothesis test we actually would like to define, what it's supposed to do and what the basic ideas are. Then I will very briefly touch on the technical side, on the loss asymptotics, but I will not go into the calculations and the proofs that are in my paper, because that would really derail things quite a lot, I think. And finally, I will show some simulations to illustrate the properties of the hypothesis test. And I will show 3 applications. And I would like to mention those beforehand, because those are kind of the motivation why I think this is worthwhile doing. So these are, I'm looking at 3 kind of typical systems where such a test is useful, namely one being the mean for data on a manifold, on a positively curved manifold. The second example being nonlinear regression. And the third example being clustering algorithms with centroids like k-means or Gaussian mixture clustering, which is actually the example I will be presenting. And I will present only always one specific example, but I think they are actually kind of prototypical for these types of systems and illustrate the types of problems that can arise. Okay, so, but now let's first start at the beginning. And I'll start with some examples for data on manifolds, because we will use the setting of data on manifolds, and some of you might not have had very much contact with that. So I'll give some examples here of data types which are best represented on a manifold and cannot always be well represented in some kind of Euclidean space. Because in some cases they can actually fill a lot of the manifold, and then curvature becomes important and the topology of the manifold becomes important, and one cannot simply very easily go to a Euclidean representation. And so the simplest example I could think of is directional data, for example, for animal movement or all kinds of other examples, which is usually on a circle or on a 2-dimensional sphere, depending on whether it's direction in the plane or direction in space. Another larger class of data are geological, atmospheric, or astronomical data, which are on an S2, which is either the Earth's surface or, again, a kind of a, well, astronomical data is often directional data on an S2, where the S2 is then the directions of the night sky. Another important example are joint movements, which are important for robotics, for prosthetics development, or for medical diagnostics. And joint movements are often represented in terms of rotation groups. So SO3, for example, which then register the rotation of certain bones relatively to each other also. There are covariance matrices, which are symmetric positive definite matrices. And the space of symmetric positive definite matrices has kind of a cone shape, so it's also a nonlinear space in general. Well, depending on the geometry you look at. And another kind of example are landmark shape spaces, where one tries to represent a shape in a vector space by specific landmarks. So, for example, for facial feature detection, this is often used. Landmarks could be like the inner points of the eyes, the outer points of the eyes, the center, the tip of the nose, the tips of the sides of the nose, and so on, right? So you have these several points, and then you would like to factor out translation. So you subtract the mean of all these landmarks. You would like maybe to factor out scaling, because you can have kind of zoom effects in images. So if you want to do facial recognition, you might want to factor out the scale, and that will give you a point on a sphere. And then you might want to factor out rotations, and that would give you the quotient space of the sphere, where you quotient out a rotation. So in two-dimensional space, M would be 2, and so on. So these are, in general, they can actually have degenerate regions, so they are stratified spaces, but yeah, they have a manifold part. And what all of these types of manifold have in common is that they are in generic geometries one looks at, they are positively curved. And in terms of negative curvature, there's actually a very nice, or non-positive curvature, there's actually a very nice result that, for example, the mean is unique. But in positive curved manifolds, this is not true. And right, so now let's actually talk about the mean on a manifold. On a manifold, one cannot simply add up points, because one doesn't have this linear structure or a group structure. What one does instead to define a mean is to take the minimizing point of the expected square distance. And this is an idea that goes back to Fréchet in 1947. And therefore, this is commonly called the Fréchet mean by quite a number of people. And this can be very nicely defined on manifolds, on Riemannian manifolds, where the metric here would then usually be Riemannian geodesic distance. So the length of shortest curves between 2 points, in a sense. One can then define a very important tool, the exponential and the inverse log map. So the exponential map maps vectors in a tangent space at some reference point. So let's take mu here, the population Fréchet mean, as a reference point. We have a tangent vector here. And now we want to define a point on the manifold corresponding to this tangent vector. So what we do is we take the geodesic that has at mu the tangent vector as its tangent vector. So that starts out in the direction of this blue vector. And then this red arrow follows this geodesic. And at the tip of this arrow, this is the point we're looking at. And the length of this red arrow, so this geodesic segment, is the same as the length of this tangent vector. So this is very important. This exponential map and the inverse log map, they are length preserving, right? They map lengths of vectors to lengths of geodesic segments. And so these names, exponential and log, should not be thought of as changing the length in any way. They actually stem from matrix spaces, where this would be the matrix exponential or matrix logarithm functions. So these are kind of historical names. So don't be misled by these names, right? They are length preserving. And so we define the population and sample Fréchet functions with the help of these exponential functions, of this exponential map at the population mean, so that the argument is in a linear space. So we can, in that sense, represent our sample means as linear vectors in the tangent space of the population mean. And the population and sample means in this tangent space are, well, 0 for the population mean by definition of the tangent space at mu. And we would call the sample Fréchet means mu hat n. And so when we use nu, that will always mean that we look at the point in tangent space. And if we use mu, this means just the point on the manifold mapped by the exponential map, okay? So in this way, we distinguish whether we are looking at this point in terms of a point in tangent space at the population mean or as a point on the manifold. Okay. And now let's look at the generalization of this concept. And this is the concept of M estimators. So here we look at the data space Q, say a manifold data space Q, a manifold descriptor space P, and a continuous estimating function rho, which goes from which maps a pair of descriptor and data to a positive or non-negative real number. And then we can define the so-called generalized Frechet means or population descriptors as the minimizing points in the parameter, in this descriptor space P here of this expected value of the function rho. And in this case, I assume that these might be non-unique. So there might be a finite number M global minima of this expected value function. And just to point this out very briefly, this descriptor space is quite commonly also called parameter space. However, these descriptors can be something like a Frechet mean or like a best fitting geodesic or something like that, which is not necessarily connected to a specific or to a very clearly defined parametric model, and therefore I prefer the name descriptor here instead of parameter, right? But some of you might be used to this term parameter, so you can think of it in that way. And if we look at something like, for example, the maximum likelihood estimators, those can be described in exactly this setup. So maximum likelihood are M estimators, and M estimators were actually originally developed as a generalization of maximum likelihood estimators, and they are very, very commonly used in robust statistics. So some people immediately think of robust statistics when they read M estimators, but M estimators are actually just defined via this setting of minimizing an expected estimating function. So in this sense, the setting is very, very broad, and it doesn't have to be a robust estimator is what I'm saying. For example, the Frechet mean is not robust, okay? So we are looking at M estimators just as a fairly general class of statistical estimators or statistical parameters for which we can actually easily, or for which we can set up our theory and our hypothesis test. So what we do in this setting where we have multiple population descriptors is we define local versions of this estimating function, tau I of rho, right, in a delta neighborhood of these population descriptors. And we define correspondingly local population Frechet functions and local sample Frechet functions. And then for every local sample Frechet function, we can get the minimizers, which are then local sample descriptors. Okay. So for every population descriptor, global population descriptor, we have a local sample descriptor. However, if we look at the global minimizer of the Frechet, the sample Frechet function, this is under fairly general circumstances unique. There is a uniqueness result as soon as you have some well, fairly benign regularity conditions. For example, you need something like a density, so you don't want point measures of your random variables. And so in that sense, the global sample descriptor is usually unique, but we have a whole set of M local sample descriptors, okay? So keep these two concepts in mind separately. All right, and now let's look at an example, namely a probability density on the circle which has two identical modes, which are at antipodal points. So one being 0, the other being pi, okay? And we have a cyclicity here from the right side to the left side, okay? So think of this density on a circle. And now you would think, okay, the mean should be both pi half, so plus pi half, and minus pi half. Those should be equally valid mean points for this density. And that's actually true. And now let's look at the Fréchet function. So the function we minimize here, this is the dotted black line, right? And it has actually two global minima, which are here on this at this value, which is given by this horizontal line. And now the colored lines, those are 5 different samples of size n equal to 100 I drew from this population, and I calculated simply the sample Fréchet functions, right? And so we see the sample Fréchet functions, they are fairly close to the population Fréchet function, which is quite nice. However, we see here the blue and purple sample Fréchet functions have their global minimum near minus pi half, whereas the red, orange, and green ones have their local minima near plus pi half. So they actually have only local minima at the corresponding other or near the corresponding other population minimum. So if we only see a single sample, we get a unique mean. Right? For the blue sample, for example, the unique mean here would be close to minus pi half. And we see maybe if we look at a plot of the sample Fréchet function, we see, oh, there is a local minimum here, also near plus pi half. I wonder if that's giving us any trouble. So how do we actually find out if that's giving us any trouble? Or said differently, if we have a sample for which we have a unique mean, how can we be sure that the underlying population doesn't have non-unique means? Or reasonably sure, confident, let's say. And this is what we want to test with our hypothesis test, which I will sketch now. So first of all, let's start with a wish list. The test should work for an arbitrary number of local minima, because if we have a multidimensional descriptor space, so several parameters, it might be impractical to plot out the Fréchet function over all parameters to kind of detect all local minima in any way. And so we would like to not have to fix the number of local minima in advance. The test should require ideally no knowledge of local minima positions for the same reason. And the worst error, so the question is now what should be the null hypothesis, what should be the alternative? So the worst error in this setup would be to assume that there is only one population descriptor and then use standard methods for a unique population descriptor, when in reality there are two or more. And this should then be the error of first kind. So let E be the set of global minima of the population Fréchet function. Then the null hypothesis is, that we pick is that the population descriptor is non-unique. We have two or more, whereas the alternative is that the population descriptor is unique. So if our test rejects, we can say that at the confidence level of the test, we have a unique population descriptor, and therefore we can go ahead with standard methods. And if our test doesn't reject, that tells us, well, we might want to be cautious. And then one can still see, well, maybe I can determine the possible candidates for several global descriptors and so on, right? But then one has to kind of look for more sophisticated methods, or one might actually discuss whether the parameter one is currently looking at is actually so useful, or if one shouldn't look at a different parameter. Okay, So what's the idea? The heuristic idea what to do or how the test works is as follows. It's actually kind of a simplistic idea. You have your sample and you can just bootstrap from the sample. So you do the non-parametric bootstrap by drawing with replacement from your original sample a new artificial sample of the same size. So you will have some duplicate points in there and some points will not be visited of your original sample. And then for this bootstrap sample, you can again determine the bootstrap estimator. And you can do that for several bootstrap samples for a number of B bootstrap samples. So let's say 1,000 or 10,000. And then you get a lot of bootstrap sample estimators. And the idea is, let's say we take the sample that gives rise to this blue Frechet function. Now some of the bootstrap samples might actually give us, might actually have a bootstrap mean, so might actually give rise to a mean that is near plus pi half, right? If we draw from this sample, because this sample is kind of, it's a little, it's a sample of 100 points, and depending on which points are randomly chosen into a certain bootstrap sample, the height of these minima in this Frechet function, in this Frechet function curve for the bootstrap samples will vary, and some of these bootstrap samples will actually have their global minimum near pi half. Okay. And so we will have a large number of points which are close to the, so a large number of bootstrap means which are close to the sample mean, but another cluster of bootstrap means which are close to the local minimum of the sample Frechet function. And that's the idea, right? So in that sense, in such a situation where we are actually coming from a population which has a non-unique mean, we will eventually, we might potentially find points in a different cluster here. But of course, this comes, this isn't yet a hypothesis test. We don't have a level yet and so on. We don't know really how to do the testing now. So the idea is if sufficiently many bootstrap descriptors are in another cluster, so in that case, near plus pi half, right? If sufficiently many of these bootstrap means are in this second cluster, then we should not reject, right? Because then we cannot be sure whether this is actually significant in a sense. But this obviously immediately begs two questions, namely first, how do we determine clusters of the bootstrap descriptors? And there are many cluster methods, and one could say, well, we just take any cluster methods. But the problem with cluster methods is that statistical guarantees are very rare. So it's even with k-means, you don't necessarily get very good statistical guarantees, and especially if you don't know how many clusters there are in advance, you might get into a lot of trouble. So what you would like is some kind of technique that gives you asymptotic size and power results, which ideally should be uniform over the whole distribution of bootstrap descriptors, right? So as I said, we take several bootstrap samples, usually 1,000 or 10,000 or even more. And for these 1,000 or 10,000 ones, so for this set, the distribution of this set, one would like size and power to be uniform. So to uniformly bound errors on this whole set of bootstrap descriptors. And the second question is then, what are sufficiently many bootstrap descriptors in the second cluster? And for that, we need an asymptotic size result for the test statistic. And that's what we need our loss asymptotics for. Okay, but we start out with the question of determining clusters. So as I said, we need some kind of a reliable way to identify clusters. And so what we do is we only look at distances of the bootstrap descriptors to the sample descriptor. So this is extremely restrictive, right? We have a multi-dimensional parameter space, and we boil this down to a one-dimensional descriptor, one-dimensional positive descriptor. So we might potentially lose a lot of power. And so, yeah, we trade in this power for nice asymptotic results. So this is kind of the trade-off we make here. And if we have one-dimensional data from the outset, a typical histogram could look like this. So this would be on the left-hand side near 0 would be the cluster containing the sample descriptor, and the cluster around 1 would be some kind of a second cluster. And so one could say, okay, well, the cluster containing the sample descriptor, this is kind of a falling slope. And then we have, again, a rising slope and falling slope. So we would like to start here at the beginning of the first rising slope in this distribution and count every point that comes after that. So all the dj that are larger than this specific value here. However, if we have higher dimensional parameter descriptor space, what we get here is that even the cluster which contains the sample descriptor starts out with a rising slope. And this is due to the polar volume element, right? R to the dimension -1 times dr, right? If you go to polar coordinates. And this will lead to a rising slope, which is ever more pronounced the higher your dimension is. So actually what you will have is a rising slope and then falling slope for the cluster which contains the sample descriptor, and then again a rising slope and falling slope for the cluster for every other cluster. So the idea is now the method we set our sights on actually determines slopes, rising and falling slopes. So this is actually a method that's geared towards identifying rising and falling slopes in a probability density, if you have a sample from this probability density. And this goes back to Göttingen and Walter in 2008. And what we are looking for now is the next rising slope after the first falling slope. So we don't take the first rising slope, because that can actually be the cluster which contains the sample mean. And even if this right-hand cluster didn't exist, we would have one rising slope. But we take the first falling slope, and then as soon as we detect a rising slope at some point, the leftmost point of this potential rising slope detected by this test will then be the starting point after which we count all the number of bootstrap descriptors for our test, right? So then here we would potentially find 0.65 or so as the starting point, and every value of dj which is larger than this 0.65 would be counted. So all of the points in this cluster here would then be counted. Okay, so now we know how to identify which points are in a different cluster than the sample descriptor, which bootstrap descriptors. Now the next step is how many points are necessary to not reject. And for that we need our loss asymptotics. And so one could naively, for example, think if 5% of the points are in this, or let's say 4% of the points are in the second cluster, in the right-hand cluster, then maybe we would reject the test at a 95% level, because 4% is less than 5%. And however, we don't have any theoretical result to back this up yet, and we might actually be mistaken about this. So let's look into this. Yeah, as I said, I will spare you most of the gory details, and just hopefully give you an idea what we're how we are going to approach this. So we denote the minimum values of the population and sample Frechet functions of these, and we call these minimum values losses. Okay, so if the Frechet function is actually the square distance, and so the descriptors are means, one would call those variances. This is the reason why I use the letter V here. So you can think of them in a sense like variances in a way, but they are not necessarily really variances of the descriptors or the data set. So be careful with this idea. So what we look at is a vector of all those M local losses, and the population losses are all the same, of course, by assumption, right? By assumption, these values, we have M global minima, so the function values at the global minima are all the same. And then we denote this vector of local Frechet functions at the population mean like this, and we define its covariance matrix. So covariance of tau is this vector of local Frechet functions near those global descriptor values. And then what we can show is the central limit theorem, that the sample loss vector minus the population loss vector, and here the population loss vector, as I said before, all the entries are the same, so it's V times a vector of ones. And we look at this difference, we rescale it with square root of n as usual in this central limit theorem, and then converges in distribution to a normal distribution whose covariance is the covariance of tau. Okay, and so this is now an m-dimensional multivariate normal distribution where m is the number of global minima of the population Frechet function. Okay, this is not the dimension of the parameter space. This is the number of minima we have, because those values of the Frechet functions are always real, right? So one-dimensional, no matter what the dimension of your parameter space is. Okay. So don't get this m confused with the dimension of the parameter space. And so consequently for two of the, so taking I and j, two of these local minima, taking the difference of these loss values will also converge to a normal distribution. This is just a marginal, if you will, of this multivariate normal. And the variance will be just the variance of the difference between tau I and tau j. So this is a central limit theorem, and then we define the bootstrap quantities. So we can define a local bootstrap, estimating function here around the local bootstrap, around the local sample means, local sample descriptors, sorry, here. And we can define the local bootstrap Frechet functions, and then the local bootstrap losses, and the local bootstrap loss vector again. And we can, again, play the same game. And in the end, we will also want a result on the variances and so on. And after all this theory is done, what we get is an asymptotic result for the quantiles. So here, this is a kind of a difficult thing to really explain what we mean here. So let's say here we look at this set A alpha epsilon ij. So here Eij is Ei minus Ej. So what's here is really Xi minus Xj. So we say that Xi is basically, so this is in a small interval of between 1 and 1 plus epsilon. So it's roughly 1, this right-hand side here, right? Later on, we want to send epsilon to 0. So let's, for the time being, assume that we had equal to 1 here, right? Just to make this a little simpler. So then what this here is 1 over the alpha half quantile of the normal distribution of the limiting distribution of the central limit theorem here, right? So Q is the standard normal quantile, and this is the standard deviation, and this is the square root of n from the central limit theorem. So what we have here is 1 over the quantile of alpha half quantile. So what we have is xi is equal or is roughly equal to xj plus this quantile, but since it's an alpha half quantile and alpha is smaller than 1, so alpha is usually something like 0.05, right? So your typical test level. This is negative, right? So we have that xi is smaller than xj by this alpha half quantile of the central limit limiting distribution, okay? And then we take an intersection of all these sets for all j's. So here we say our ith minimum is lower by a distance of the alpha half quantile than all the other minima, okay? And not exactly, all the other minima are in a thin band of 1 plus 1 to 1 plus epsilon, right? So all, if our minimum I is down here, and this here is the distance of the alpha half quantile, so the inverse of this term here, then we have a band here in which all the other minima lie, okay? If you think of this as a one-dimensional function. And here is a corresponding set where we only have smaller equals. So there we say, okay, if our ith minimum is down here, all the other minima are at least up here or arbitrarily higher, okay? So in this sense, these are a sort of tail regions of the asymptotic distribution, okay? And so what we are now saying is that under these technical assumptions and using our central limit theorems, the probability that this ith loss is smaller than all the other losses by at least the alpha half quantile, and then summed over all the i's, of course, these probabilities summed over all of the minima, is in the limit of sample size going to infinity smaller or equal than alpha. And if m is equal to 2, so if we have exactly 2 minima, this is actually exactly equal to alpha. For larger number of minima, it might be smaller, and but this is good enough. In this setting, this is, I mean, what we want to make sure is that our test can be conservative, but it shouldn't be liberal. So the size might in some cases be the true size might be kind of smaller than the theoretical size. Or the true confidence level might be kind of higher than the theoretical one, but it shouldn't be lower. And now the second part is that for the bootstrap losses, so the probability of the ith bootstrap loss not being the lowest, so crossing with either one of the others, right? Given that the ith bootstrap loss was smaller than all the others by this alpha half quantile, and with this small strip, right? This probability times 2 is in the limit of this strip here, strip width going to 0 and sample size going to infinity, larger or equal than alpha, okay? And so this, what we finally get is that asymptotically twice this probability, so the bootstrap, the probability of a sampling into another minimum, right? Because if this ith minimum is no longer lower than all the others, so if either one of the others crosses and becomes lower than the ith minimum, the global descriptor will be at that point, right? So sampling into another cluster, the probability of sampling into another cluster is larger or equal than this probability of actually being so deep into a single minimum in the first place. And here is this important factor 2. And this is again in the case m equal to 2. So if you have exactly 2 minima, it's kind of a symmetry factor. But and therefore for m equal to 2, we have equality here again. So for m equal to 2, we actually get exactly the size. For larger number of minima than 2, our test will become increasingly conservative. Okay. And so from this result of the convergence of quantiles, we can derive our rejection region, namely our test rejects if less than alpha half times b bootstrap descriptors are in another cluster. So in the case, if we take 1,000 bootstrap resamples and we take an alpha of 0.05, so the typical 95% confidence level, then we actually need to have less than 25 points in the second cluster before we can reject. So in the example I gave you before, where we had 40 points or 4% of the points in the second cluster, we could not reject the null hypothesis that the mean might actually be non-unique. So this factor of 2 is really something we only get out with the asymptotic theory. So this is kind of, for me, really kind of the most striking illustration why it's important to do this properly. Right, so let's just very briefly remember the hypothesis test, look at some simulations, and then the applications. So the null hypothesis is that we have a non-unique descriptor. The alternative is that our descriptor is unique. The test statistic is 2 over the number of bootstrap samples times the number of bootstrap samples where the bootstrap descriptor is further than d plus away from the sample descriptor. And d plus is this onset of the rising slope in these histograms I showed you. And then we reject if the test statistic t is smaller than our alpha, and we can give as a p-value the minimum of 1 or the test statistic value. So the test statistic is already built in such a way that it's basically a p-value. Okay. And now let's look at the exact example I showed you before. So one-dimensional data space, a circle with 2 modes, which are antipodal. And here we have sample size 30, 100, 300, and 500. These are PP plots where we just do p-values. So we have run 1,000 tests, each one with 10,000 bootstrap samples. And so the p-values are plotted against the uniform quantiles, theoretical uniform quantiles. And we see here they follow the theoretical diagonal already quite well for small p-values at n equal to 30. And small p-values is really the region we are interested in for the test, okay, for hypothesis testing. And we see, of course, for larger n, this even holds for all the p-values very nicely. So this is exactly the case n equal to 2, and there we have the test size actually matches the theoretical size asymptotically. Now, same thing for a 2-dimensional data space. Here we take the sphere, and we have a like a Gaussian distribution around the equator. So the north and south pole will be equally valid mean points. We see here n equal to 30 is not sufficient, right? The p-values are underestimated, especially the low ones, so that's bad. But for n equal to 100 or higher, we get nice results. And as I explained, our test size guarantees are only asymptotic. So small sample size will always be a problem for asymptotic quantiles. There's just no way out of this. And what you can see if you look very closely here is that you have a step here that some very small p-values are actually underestimated to 0. And this is if the second cluster is too small, has too little points for our multi-scale slope detection test to detect it. And this is usually when it becomes smaller than 30 or 20 points. So this means you need to take a large enough number of bootstrap samples. And here in this case, we only took 2,000 instead of 10,000 bootstrap samples. Therefore, we see this little dent here. Okay. Right, but for a 5% confidence level, so for alpha equal to 0.5, no, 0.05, this still works well. And here I look at power of the test. So I have 2 modes on a circle, and now they are not not necessarily exactly antipodal, but one of them moves, the center of one of the modes moves along the circle. And here on the x-axis is the distance in radians. And here the curves show the rejection ratios of the test. And ideally, if this distance is, well, not exactly 0, it should jump to 1, right? And we see the larger our sample size is, the sharper these curves actually get. We jump to a rejection ratio of 1 pretty quickly, and rejection ratio of 1 means that our test really reliably detects that the mean is unique, which is the case if the 2 modes are not completely antipodal, because then they are kind of, for example, both on modes are a little on the right side, then the unique mean will actually be on the right side of the circle, right? So this is quite nice, and this also conforms to our expectation. All right, and now I have just enough time to tell you about the applications. So the first one are female sea turtles leaving their nest on the beach after laying eggs. And they want to actually go to the east toward the rising sun, because there's the seashore, right? They arrive on the evening following the sun, and then after laying their eggs, they depart in the morning and follow again the sun back to the sea. But some unfortunate turtles run in the exactly opposite direction. And what we see in this data set here, n equal to 77 in this case, so they looked at 77 sea turtles. What one can see here, we have 2 modes, as in our example before. And actually then here, if you look at the histogram of distances, we see, okay, there are several other modes. It's not as clean cut as I showed you before, but there are significantly rising slopes, and therefore the test does not reject. The p-value is even quite close to 1. So we cannot rule out the possibility that the mean direction is actually non-unique. And so, okay, one could say, if you see this data, this bimodal structure, you wouldn't calculate the mean. However, maybe you have agreed with your experimenter before the experiment that you would like to know the mean direction and the variance of the turtle direction choices. And then only after taking the data, it turns out that some turtles somehow get the wrong idea. So in that case, this test could actually tell you, well, for this data set, the mean is actually a problematic quantity. Second example, non-linear regression. So we looked at the growth of actin fibers in blood platelets after setting down on the surface. And these actin fibers make the blood platelets stiff, so the wound closure becomes more stable. And this is measured in the total length of all the fibers. And the measurements are really very, very noisy, because the images are kind of very difficult quality and so on, right? So this is really close to the resolution limit of the microscopes. And so the extraction of these fibers, the detection of these fibers isn't always that simple. And therefore we have kind of noise data. So what we would like to fit is an exponential saturation model. So kind of a, at some point, when the growth starts, it kind of settles exponentially into a finite value, and not exactly a finite value, actually a linear function. So we allow for some kind of slower process, which we just approximate as a linear function, which we don't care about. So we are interested here in the quick buildup in the beginning. So the most important parameter here is θ2, the exponential settling time. And we can formulate this. This is least squares regression as an M estimation problem like this. And here I have two examples. So in this example, the test does not reject. The black curve is always the best fit. So this is the sample estimator, the sample parameter, right? The best fitting curve. And the blue curve is one of the curves from the other sample, which is pretty central from the other sample. So drawn from the other cluster of curves, right? Because in both of these cases, we have a second cluster. And in the first case, the second cluster is large enough, so the test does not reject. So this might actually be non-unique. And we can see this blue curve takes quite a lot longer than the black curve to settle down. So here we have actually a non-unique result for our θ2, which we should take into account. In the second case, we see the test does reject. However, the best fit is not really very credible when we look at the description of the experiment. So what we actually had to do in the paper then was restrict our parameter space to make sure that we were near zero or at zero at say minus 30 seconds or so. So the movies were started at the point in time when the platelets settled down, so we could be sure that this black curve here actually doesn't work. But we just don't have all of this zero data in front here, so therefore this doesn't influence the fit. So this is then something we healed by this restricting the parameter space. But alone from this test, one wouldn't immediately expect that, because here in this case, the test rejects and the test tells us this black curve is actually unique. However, looking at the black curve, we would say, well, it's not good. Okay, and then the third example is a very classic data set, the iris data set from the R datasets package. We look at 4 blossom features for iris flowers, 3 species of iris, each of them 50 blossoms. So n is equal to 100 in a dimension 4 space. And we have 3 clusters of size 50. Or theoretically, 3 classes of size 50. And I will look at the first and second principal component because those are very nice to see the cluster separation. So the species label here show that if you would just, for example, do a t-test or so, these t-square test, these species would all be very clearly distinct. However, the cluster for the blue species is very well separated from the other 2, whereas the black and gray clusters are very close by, and it's not so clear how well they can be actually separated. So that's the difference between hypothesis testing and classification. And so what we did, it was a Gaussian mixture clustering, so just a simple MLE and EM algorithm. And we get this result here, where the stars are the cluster centers, and we just colored the points according to the best fitting cluster center. Those are very, very close to the species labels, actually. We have less than 10 points which are misclassified. Very nice. However, if we do our test and we take these cluster results as our descriptors, then we look at clusters of descriptors, we see we have alternate clusters. And this is because these points down here are often classified into the gray cluster, and these points up here are often classified into the black cluster, depending on the bootstrap samples. And therefore, the test here does not reject. It has a p-value of 1. And this means we cannot rule out that our clustering is actually unstable. It's and therefore this cluster result is not unique and cannot be taken, or I think it should not be taken at face value as kind of a sign that, okay, well, Gaussian mixture clustering reproduces the theoretical classification, theoretical classes. And if we do this actually with two components, we get a very stable classification, and our p-value is 0 of the test, and one cluster is always the blue one, and the second cluster is always the joint black and gray one. So in that sense, one can here use our test as a kind of a model selection criterion, which would prefer a model with 2 Gaussian mixture components over a model with 3 Gaussian mixture components, because the fit for the 2 mixture components is reliable, whereas the fit for the 3 mixture components is unreliable. Yes, and I think I hope this convinces some of you that this is actually useful in practical situations. And with that, I end my talk. Thank you.